Hi everybody, welcome to Anode Academy, and today we are going to start with chemical kinetics. Okay, so what do you mean by the word chemical kinetics? Chemical kinetics is very simply learning the kinetics of any chemical reaction. Okay, learning the kinetics of any chemical reaction. Now, the literal meaning of the word kinetics is speed or rate. Okay, so this is a field where we try to learn the speed of any chemical reaction. We try to determine the rate of any chemical reaction. Why? Why do we want to know the speed or rate of any chemical reaction? Is to have some idea, okay, to understand the mechanism of the chemical reaction. So it will give us some idea of the mechanism which can be used for various applications. Now, what are those applications? I'll discuss that shortly. So this is a very brief introduction of what chemical kinetics is and what it can be used for. Okay. Now, can it be used to learn all the types of chemical reactions? No. Chemical reactions, again, can be classified into three types based on their rates. Okay? So, classification of chemical reactions based on their speed. Based on the speed, the chemical reactions are classified into three. First one, quick reactions. Quick reactions, meaning they happen very quickly. They're very fast. Okay, what is example? Example of a typical quick reaction is the neutralization reaction. Neutralization reactions. For example, you have a very strong acid like HCl, and you mix it with a very strong base, NaOH. The moment you mix them together, what happens? You get a salt of NaCl and water. This is relatively very quick. Okay, so this is one example of quick reaction. Another example, precipitation reactions. Precipitation reaction. Please note, this has been asked previously. I'll tell you how, but this example, what I'm going to write over here, has been asked previously, okay? PYQ means previous year question. Okay. So another example is AgNO3. The moment you add silver nitrate to NaCl, what happens? You get a precipitate. You get a precipitate of silver chloride suspended in NaNO3. So this is a precipitation reaction. So you notate precipitate by a downward arrow. This is also very quick. Another general example, explosions. So these are certain examples of quick reactions. Very quick reactions. Next one, noted down, two very slow reactions. Slow reactions. Slow reactions. Slow reactions happen very slowly, of course. For example, note down the examples. Combination of combination of hydrogen along with oxygen O2 to form water at room temperature. So this is important, at room temperature. So this does not happen very easily under room temperature conditions. It requires different temperatures and different pressures apart from room temperature conditions. So if this is taken at RT, room temperature, this is very slow. Another example is rusting of iron. This is also a previous year question. This has been asked. Rusting of iron. So what happens when iron is exposed to air, which has moisture? It forms rust. Yeah, it forms rust. So rust basically is iron oxide, Fe2O3. This is formed. This is a very slow process. Another example is the conversion of coal to diamond. Coal to diamond. Again, this takes years and years for this transformation to happen, and this is slow. Okay? So, whether it is a quick reaction or it is a slow reaction, we cannot determine the kinetics of these two types of reactions using the principle that we are going to learn. I repeat, these two, quick and slow, meaning very fast and very slow reactions. Okay? Whatever principle we are going to learn a lot of them. None of them can be applied to very quick or very slow reactions. Not applicable. Not applicable. We cannot learn the speed of these reactions. We cannot learn the rate of such reactions. But the principles that we learn can be applied to reactions which proceed with a moderate speed. Which proceed with a moderate speed. Example, ester hydrolysis. Ester hydrolysis. What happens in ester hydrolysis? Let's say you have some ester. In the presence of water, it becomes an acid and an alcohol. Very easy example. This is ester hydrolysis. One example of a reaction which proceeds with a moderate speed. Decomposition of H2O2. Decomposition of H2O2. What is H2O2? Hydrogen peroxide. So hydrogen peroxide decomposes into water and oxygen. Moderate speed. Again, another example is the formation of NH3. Formation of NH3, a very famous process. What's the name of the process? It's called the Haber's process. Haber's process. Okay, where nitrogen combines with hydrogen to form NH3. So let's balance this. NH3. Okay. So these are some typical examples of reactions that proceed with a moderate speed, and we can apply the principles of chemical kinetics over here only. So whatever we are going to learn, the concepts are applicable to those reactions which proceed with a moderate speed. Again, let me tell you that there are millions and millions of reactions. You cannot categorize them into three and start mugging them up all. That's not at all possible. So this is to give you a basic idea that if you get a statement question For example, you have an option where there is rusting of iron. You have an option which is very slow. You have an option where there is precipitation, which is very quick. And you have a third option like ester hydrolysis. And the questioner asks, which can be used to determine the rate of a reaction? You will pick ester hydrolysis. Okay, so this gives you the very basic introduction to chemical kinetics, that it allows us to learn the rate of reactions. But can it be used to learn the rates of the reactions which are very quick? No. Can it be used to learn the rates of the reactions which are very slow? No. It can be used to learn the rates of the reactions only when they proceed with a moderate speed. Only when they proceed with a moderate speed. Okay. Now, why do you want to learn the chemical kinetics of reactions? As I said, you have certain applications, and some among them are: one, to calculate the expiry dates. Expiry dates of, let's say, pharmaceuticals, packaged foods, etc. So you can use the principles, the equations, the concepts, etc. to calculate the expiry date. You can tell the customers that whatever you have bought is useful to you till this and this date. Till so and so date is what you can tell. Okay. Now, industrial applications like catalysis studies, there also you can apply them. You can add a catalyst and you can see how the process has increased its rate. For example, you have Haber's process over here, nitrogen combining with hydrogen to give ammonia. You can add certain catalysts to it, for example, like iron, and you can see how the rate is changing. If your rate is improving, you can build upon this reaction, and then you can come up with a reaction which is more efficient than the reaction without a catalyst. So it can be used for catalysis studies as well. Okay, so this is a very brief introduction of what chemical kinetics is. So the only takeaway from whatever we have learned over here is chemical kinetics is where you learn the speed or rate of the reaction for moderate reactions only, for reactions that proceeds with moderate speed only, not for reactions that are too slow and not for reactions that are too quick. Okay? Yes, so that's it. Now, let's get into the main topic. Please note down the heading, rate of a reaction. Rate of a reaction. What is the rate of a reaction? So simply, if we have to express it in a mathematical formula, rate of a reaction, or you can also call it speed of a reaction. Okay. So I'll write it as ROR. ROR. Okay. So ROR, very important, is the changes in the concentration of species. Changes in the concentration of species. I'll explain which species. Changes in the concentration divided by changes in time. Changes in concentration divided by changes in time. Now, most commonly, concentrations are written in molar units. So we need to know units very thoroughly. In exams, people do change units little by little, and then they might confuse you. So you should have a very good grasp on the understandings of units as well. Okay. Concentrations are usually written in molar. So changes in concentrations is going to be molar, changes in time per second. Correct? It is molar by second. Changes in concentrations in molar by changes in time, seconds, which means molar per second. Now, 1 molar is written as moles per liter. Okay. So it can also be written as moles per liter per second. 1 molar is equal to 1 mole per liter. Okay. So the units of rates of a reaction is always in moles per liter per second or molar per second. Now, this is the case when you have systems under aqueous conditions. For example, you have aqueous suspensions. Aqueous suspensions means where you have certain chemicals that are dispersed in water or any other solvents that are liquid in nature. Therein you can calculate the volume and you can calculate moles per liter per second. Aqueous systems. Let's say you have gaseous system. Gaseous systems. For gaseous systems, it's not moles per liter per second. Here, the changes in concentrations are expressed in terms of pressure. Okay, so it is changes of pressure divided by changes of time. So the changes of the pressures can be either in atmospheric pressure, so atmosphere per second, or it could be in bar, BAR, which is one among the units of pressure, bar per second, etc. Okay, so when you have aqueous system, which is most common, your units will be expressed as moles per liter per second. And when you have gaseous systems, it's going to be pressure per unit time. Okay. Now, whose concentration is that we monitor? Whose concentration is that we monitor? So, if you have a reaction, for example, you have a reactant R. Upon some reaction, it becomes products. So this is a reaction simplified as reactant R giving product P. You can write the rate of the reaction both in terms of reactant and in terms of product. Very important. For example, if you have to write the rate of the reaction in terms of the reactant. So how will you write it? You will write it as changes in concentration of the reactant. Concentration of any species is written inside square brackets. Okay. Changes in the concentration of the reactant per unit time. Changes in time. Okay. To understand it better, let's say that initially you had 20 units of some reactant at T is equal to 0. Reaction has not begun. You had 20 units of reactant. Okay. And you don't have any products. Okay. Now, after some time, as the reaction proceeds, some amount of reactant reacts. And let's say now it has reacted 5 units and it has become 15. And this has become 5. Product has been formed. So if you can see that this is your initial concentration and this is your final concentration. This is your initial 20 units. This is your final 15 units. So the changes in the concentration of R from the example that we have written is 15 minus 20. Final minus initial always. Okay, so changes are always measured as final minus initial divided by changes in time. So it was T is equal to T and initially it was 0. So this is going to be minus 5 by T. This is going to be your rate, this much of units, whatever it is. Now, what you have to understand is always rate is expressed as a quantity which is positive. Very important. Very, very, very important. Rate of any chemical reaction that you have is always going to be expressed as a positive quantity. Whether it is a rate of the reaction with respect to reactant, or if it is a rate of a reaction with respect to the product, whoever the species is, it is always going to be positive. But see, what you have got now is a quantity which is negative. So in order to make it positive, you put a minus over here. You put a minus over here such that the resultant rate becomes positive. Minus of minus is positive. Okay? So what you have to understand over here is when you express the rate of the reaction with respect to the reactant, rate of the reaction with respect to the reactant, you will have a negative sign over here in order to make the rate positive. Okay, so the changes in the concentration of R, very small changes are determined and written as D, changes, small letter D, meaning changes of concentration of the reactant by changes in time, SROR. Okay, don't get confused over here. It is changes of time. Changes in time. Changes in time. Okay, so this is with respect to the reactant. You have a negative sign over here in order to make the overall rate positive. Now, if we have to write it with respect to the product, how do we write it? It is changes in the concentration of the product divided by changes in time. So let's see how the product has changed. So this is the final concentration of the product. This was the initial concentration of the product. So final is 5 minus initial is 0. Final time was t, initial time was 0. So this is 5 by t and this is positive. This is already positive as it is increasing, right? The product concentration increases, but the reactant concentration decreases because reactant is being consumed. Correct. So the rate of the reaction with respect to the product is going to be plus dP by dt. Changes P notating the changes of the product. Okay, very important. Whenever you express the rate of a reaction, always understand that it is concentration changes of certain species. It can either be the changes in the reactant or it can be the changes of the product. Whatever the species is, the rate is always going to be positive, always positive. So in order to make it positive, we add a negative sign to the expression where reactant is there, because as time proceeds, the reactant concentration is decreasing. So to make it positive, the rate of the reaction is minus D concentration changes of the reactant by dt. And for product, it is just dP by dt. Okay, so this is how you calculate and you determine the rate of the reaction. All right. Now, apart from the rate of the reaction, that is the overall reaction, there are certain terms called rates of disappearance and rates of appearance. So let's try to understand what that is. Let's try to understand what that is. So please note down the heading. Note down the heading. Rate of disappearance. Rates of disappearance. So there are different names. Okay, it can be called rates of disappearance. In questions, you can also get it as deformation. Calculate the rates of deformation. Or it can be written as consumption. Calculate the rate of consumption, calculate the rate of deformation, calculate the rates of disappearance. There are many names, all have same meanings. Okay. Now, if you see this reaction, who is disappearing? Who is being deformed? Who is being consumed? R. Correct? The reactant is being consumed. For example, let's say that I take a typical reaction. 2A giving 2B plus C. 2A plus 2B giving, 2A giving 2B plus C. So on the reactant side, you have 2A, and on the product side, you have 2B and C. Now, whatever is written over here, these numbers, these are called stoichiometric coefficients. Stoichiometric coefficients. Stoichiometric coefficients. Okay. So if the question is to just write the expression of rate of disappearance, you do not consider the stoichiometric coefficient. I repeat, if the question is to determine the rate of disappearance, you do not consider the stoichiometric coefficient. It's very easy. Rate of disappearance for this reaction, whatever we have written, rate of disappearance. Who is disappearing? A only will disappear because that is a reactant. That is simply equal to, as it is a reactant, you will put a negative sign, which we have already discussed over here, minus concentration changes of the reactant by time. Here the reactant is A, so it is minus dA by dt. That's all. That's all. You write the changes of the reactant with the changes in time, ignoring the stoichiometric coefficient. That's how you calculate rate of disappearance. Now, let's say that the question is to find the rate of appearance. Appearance. Now, instead of appearance, they can also ask about formation, product formation. Okay. So who is being formed here? The products are B and C. So we have two products. So rate of appearance with respect to, let's say, B, which is one among the product, is you ignore the stoichiometric coefficient. Do not take that into consideration. It's simply changes of concentration of B with time. That's it. You have one more product. Rate of appearance with respect to C is very simply concentration changes of the product C with time. That's all. Okay. So if they ask you about rate of disappearance, rate of appearance, all that you have to do is you check whether it is a reactant or a product. If it is a reactant, you must put a negative sign, and then you express changes in the concentration with changes in time. No stoichiometric coefficient considered. If it is the rate of appearance, you put plus changes of the concentration with time. That's all. Now you might be confused of what is the difference between rate of a reaction, rate of disappearance, rate of appearance. So note down the next point. How is it different from rate of a reaction? How is it different from rate of a reaction? Rate of a reaction is very simple. You just, for example, we have the same reaction. 2A giving you B plus C. When you write the rate of the reaction or speed of a reaction, you have to consider the stoichiometric coefficient. Write it over here. Stoichiometric coefficients are considered. How are they considered? The rate of the reaction over here with respect to A. Rate of the reaction, ROR, with respect to A is you have to take the reciprocal of the stoichiometric coefficient, which is 1 by 2 into A is on the reactant side, so changes of the concentration of A with changes in time. That's it. Now, rate of the reaction with respect to B. So please see that earlier we did not consider the stoichiometric coefficient. And when stoichiometric coefficient is not considered, you call it rate of disappearance. But if stoichiometric coefficient is taken into account, you call it rate of the reaction, and they are different. They're different in principle. Okay, so you have a 2B. So rate of reaction with respect to B is you take the reciprocal of the coefficient, and being the product, you will put plus changes in the concentration of B with respect to time. Rate of reaction with respect to C, the stoichiometric coefficient is 1. So it's just plus changes in the concentration of C with time. Okay? So I hope you have got the understanding of what is the difference between rate of disappearance, rate of appearance, and rate of reaction. Okay, so to summarize, if I want to write, let's say I take a model reaction where AA plus BB gives CC plus DD, where small letter A, B, C, D, these are all stoichiometric coefficients. These are all stoichiometric coefficients. Now, if I want to write the expression of rates of reaction, so rates of reaction can be written with respect to A, B, C, or D, with respect to the reactants or products. How do we write it? We have to take the reciprocal of the coefficient, and then changes of the concentrations with changes of the time is multiplied. Correct? For example, with respect to A, it is 1 by A minus dA by dt. That is with respect to A. That's all. With respect to B, what is it equal to? 1 by B minus dB by dt. Changes in the concentration of B with T. You can put A also in square brackets. Okay. With respect to C, it is 1 by stoichiometric coefficient C into changes of the concentration of C by changes in time. With respect to capital D, the product, it is 1 by D, changes in the concentration of D with changes in time. So the rate, whether it is written with respect to A, whether it is written with respect to B, C, or D, whatever the species that you consider, the rate of the reaction will always be the same. Please understand. For example, if you got the rate with respect to A as 5 moles per liter per second, with respect to a different species, let's say B, this will also be 5 moles per liter per second. With respect to C also, it's going to be 5 moles per liter per second. With respect to D also, it's going to be 5 moles per liter per second. So whoever the species is, whether it is A, B, C or D, the rate of the reaction will always be the same. Very important. Okay, rates of the reaction are same with respect to all the species that are present in the reaction. Okay. Now in the same reaction, if I have to write the rate of disappearance, who will disappear? Species A will disappear because it is a reactant. So rate of disappearance with respect to A. What is it? It is just minus concentration changes of A with T. You do not take the stoichiometry into consideration. That is the difference. Here you have the coefficient. Here you don't have the coefficient. Let's say I have to write rate of disappearance with respect to B. It is minus dB by dt. No stoichiometric coefficients considered. Similarly, rate of appearance or formation of C is, as being the product, you will put plus dC by dt. And finally, you have rate of formation of D. Again, it's on the product hand side. So it is dd by dt. That's it. Okay. So you have to have a very good understanding of what is the difference between rates of the reaction and rates of disappearances and formations of each of the species. Okay, so this is the first session of chemical kinetics. I'll stop over here. Let's do 2 questions. Okay, please note it down. Question number 1. Question number 1. First question. In the reaction of formation of SO3 by contact process. So the process is given 2SO2 plus O2 giving 2SO3. The rate of the reaction was measured as minus dO2 by dt is equal to 2.5 into 10 to the power minus 4 moles per liter per second. Question. The rate of the reaction in terms of concentrations of SO2 in moles per liter per second will be option A, 1.25 into 10 to the power minus 4, 2.5 into 10 to the power minus 4, C, 3.75 into 10 to the power minus 4, and D, 5 into 10 to the power minus 4. Okay, please pause the video and try to do it by yourself. So here the question says that you have certain process where the reactants are SO2 and O2 and the product is SO3. And they have measured the rates of the reaction They have measured the rates of the reaction with respect to O2, and they say it is 2.5 into 10 to the power 4 moles per liter per second. And the question is, what is the rate of the reaction in terms of SO2? So what is the answer? The answer is option B. Why option B? I already said that whatever the species that we consider is, whether it is A, whether it is B, C, or D, meaning reactant or product, whatever the species is, the rates are always going to be equal. So the question is given with respect to O2, and they have asked with respect to SO2, the rate of the reaction. It's not going to change. The rates of the reaction with respect to SO2, O2, and SO3, they are all going to be the same, and that is 2.5 into 10 to the power minus 4. So the correct answer is option B. Correct answer is option B. Okay? One more question, please. For a reaction, 1 by 2A giving 2B, the rate of disappearance of A is related to rate of appearance of B by. Okay, it's a good question. So they have given some reaction. They want the relation between rate of disappearance of the reactant and rate of appearance by of the product. Okay, so note down the options. Minus dA by dt is equal to plus 1 by 2 dB by dt. Option B, minus dA by dt is equal to 1 by 4 dB by dt. Option C, minus dA by dt is equal to plus dB by dt. And option D, minus dA by dt is equal to 4 times dB by dt. Okay. So how to do this problem? So whenever they ask the relations between the disappearance and appearance, etc., first of all, you write what we can express from the rates of the reaction. So what is the rate of the reaction? Rate of the reaction where stoichiometric coefficients are considered. Okay, so here the stoichiometric coefficient is 1 by 2. The reciprocal of stoichiometric coefficient is 2. So it is going to be 2 times minus dA by dt equal to, on the product hand side, you have B and the stoichiometric coefficient is 2. Its reciprocal is 1 by 2 plus dB by dt. Okay, this is what you have. Now here, minus dA by dt is your rate of disappearance. And in all the options, you have minus dA by dt on your left. So you have to express it in terms of minus dA by dt. So if I keep minus dA by dt on the left, minus dA by dt on the left, and I take 2 to the other side, it becomes 1 by 4. Plus can be avoided because it is positive only. If you put and if you don't put, that doesn't make any difference. dB by dt. That's it. So it's option B. It's option B. Yeah. So see, minus dA by dt is the rate of disappearance of A. And that is equal to 1 by 4 times. What is dB by dt? Just dB by dt, that is without considering the coefficient, that is rate of appearance of B. Okay, so that's how you do the question. Now I'll give you 2 more questions as homework. We'll be discussing the answers in the next session. Question number 3. Homework question. For the reactions, note down the question please. For the reactions 2N2O5 giving 4NO2 plus O2, the rate of equation can be expressed as, so they have given in the question that minus dN2O5 by dt is equal to K times N2O5. And they have given that dNO2 by dt is equal to K prime N2O5. So this is what they have given. And the question is, K and K prime are related by. Try it on your own. I'll give you a hint. So they have given some clue based on N2O5 and NO2. N2O5 and NO2. So you write the rates of the reaction with respect to these 2 species, substitute these values and try. Try it on your own. Okay, so the options are K is equal to K prime, 2K is equal to K prime, K is equal to 2K prime, K is equal to 4K prime. Okay. Only 1 question is needed as homework. So please note down the question. So that's all for the first session. So we have learned about the very basic concept of what chemical kinetics is, which types of reactions can be used to learn the chemical kinetics that proceeds with moderate speed. And we have learned the expressions of rates of reaction with respect to the reactant and product. And also certain terms like rates of disappearance, rates of appearance, rates of formation, rates of consumption, etc. Okay, so that is it for the session. All right, so bye-bye. See you in the next session. Do try the homework and see if you can answer, okay? Thank you.